Thank you. Okay. Hello, everyone. Thank you for joining this Rubin Science Assembly. My name is Andres Plazas Malagon. I work for the Rubin Observatory as part of the community science team, and I work as like National Accelerator Laboratory. And today, we're gonna talk about early preparation for LSSTCam and data preview 2. So basically, we're gonna go through two Rubin Science platform notebook tutorials that we have already released in preparation for data preview 2. So I guess technically today is a drop-in, but we're just gonna go through those tutorials in preparation for next week. There's gonna be a presentation by Lian Guy about DP2. So let's go ahead. We have a few announcements. One cool announcement is that Tony Tyson, who was a founding director of Rubin, was named as one of the 100 persons by the most influenced people by Time magazine in 2026. So that's cool. Another important piece of news is that the alerts are flowing there. So yeah, it's been already a couple of months, but it's always good to remind you that you can go to rubinobservatory.org for scientists, and then you're gonna have information about the alerts, the brokers that you can subscribe to, and we also have a documentation website about the prompt products, so promptproducts.lsst.io. And just related to that, if you look at the schedule of the assemblies that we've had so far, you see that there's a series of assemblies focused on this and on the brokers. So you can take a look at that because we record them. Another save the date for you is the Rubin Data Academy that has been going on for a few years now. This one is going to take place on June 22nd to the 26th. It's going to be fully virtual and held a week after the Northern Summer American Astronomical Society meeting. Another important meeting in Rubin, of course, is the Rubin Community Workshop. This year is going to take place at SLAC National Accelerator Laboratory in Menlo Park, California, USA, from July 27th to the 31st. The registration is open, but an important deadline as well is if you want to stay at the SLAC guest house, there's a reservation block that expires soon on May 11th. There are other alternative places where to stay, so they also have a deadline over there, June 15, and the registration deadline is June 22nd, unless we reach the number of people, the maximum number of people. So please go ahead to project.lsst.org, meetings, Rubin 2026. As I was saying, we have a list of the previous science assemblies, but actually next week we're going to have a related science assemblies called Early Science Updates and Questions and Answer Sessions. And actually, I would encourage you to go to that website because there's already a Google form in which Leanne will be getting your questions in advance, hopefully. Let me see if I can put it here in the chat. So go ahead and fill out that form in advance for Leanne about data preview too. So there's that. And then let me go back to slideshow. After the Rubin Community Workshop, there's going to be another workshop called Rubin 2036. Actually, I am the one leading the organization of this workshop. And basically, we want to create science cases or start asking the community or continue this process of what we're going to do with the Rubin Observatory after the LSST. So please take a look at the website. We also have the registration open and the deadline will be June the 1st. We also have a block of hotels a block of rooms at the SLAC guest house that extends from the Rubin RCW into the few days for this workshop, which is until it's 3 days. So, but the deadline for that is also May 11th. Then another important set of meetings as well is the LSST at Europe on September and October, September 27, October 2nd in Hungary. That sounds great. And then there's the third, this is the eighth one in Europe, and then the third one in Latin America, it's in November in Sao Paulo. So that sounds cool. I'm in the organizing committee for that one, so go ahead. So as usual, I want to introduce the the Rubin data products and the Science platform, and also recommending improvements in their twice a year reports to the Rubin Observatory director. So you can go to their meetings. They want your feedback, so you can either send them an email directly here to this email address, and you can use a Google form to communicate with this, and then you can recognize some of the names. These are people who are leaders in different fields of science that the LSST will do. So please use the Rubin Users Committee. And then another important resource and also is the link frameworks, which they have office hours that you can go and come and talk to them. And the link frameworks has the mission to enable the scientists by developing a scalable and productionized software algorithms in collaboration with the broader community. They have these office hours to support the community on Thursdays at the 1 p.m. Eastern Time, usually after the assemblies. And if you're part of the LSST Discovery Alliance Slack channel, you can join their Slack channel and ask questions about that. So they do also pretty cool things. All right. So I think that's it for announcements. And then now we're gonna go through these two tutorials that we have at the Rubin Science platform for RSP. The first one is gonna be about the LSST camera geometry, and the second one is going to be about data preview 2 metadata, so some preliminary data. So first of all, in case you're new to this, the way we access this is we go to data.lsst.cloud. If you don't have an account, you can go to rsp.lsst.io and then here, sign up for an account. There's a step-by-step process that you can follow. And if you have data rights, you will gonna get an account. You have LSST data rights, you're gonna get an account. So we go to data.lsst.cloud. We have three aspects. In here, we're going to focus on tutorials in the notebook aspect. So we click on that. I already signed in. Sometimes they make you sign in with CI logon or something like that, but just a heads up for that. But then one of the cool things here, and actually, hold on, view, appearance, presentation mode. Maybe that helps a little bit with the size. I'm going to increase the size here. Once you are here in the Rubin Science platform in the notebook aspect, you go to the tutorials tab, and we have a lot of tutorials that you can explore at your leisure. We have some from the simulations that before we had actual data. Those are data preview 0, data preview 1, a series of a lot of very cool tutorials with some of them translated to Spanish. And we are working hard in the community science team to produce the next set of tutorials for DP1. But so far, well, before that, there is one about solar system here, the NPC. So today, we're gonna go. I just wanted to introduce to you two of the preliminary tutorials that we have. So as a reminder, if you go to the official document for the timeline of the data releases, is called Rubin Technical Note 011. It gives us a timeline for DP2 of being available between July and September of this year. So that's the time frame that we have. Just in case you're new to this, you can go to ls.st/rtn011, and the same works with all the technical notes. Well, you need to know the number of the technical notes, but anyhow, this is the technical note that I was talking about that gives us the timeline that I just quoted. This is a useful document when you want to propose for grants and stuff like that. Okay, so that's for data preview 2. Let's go to the first tutorial of today, which it just basically introduces the how to do the plot of the LSST focal plane geometry, which can be useful for papers or just for reference because we have like almost 200 CCDs, and even myself, I have to print out the focal plane figure out which one is which. Okay, so in this tutorial, this is actually going to be based on a technical note that I wrote some time ago last year. So actually, it's kind of the code that we use for this. And you go to that technical note, and it just shows you a little bit the focal plane layout. Maybe it's a little bit hard to see like this, but basically, we're gonna learn how to do this plot today. And it shows you the different types of CCDs, the wraps, the numbers, the types, and then we ended up adding some other information, but they also shows, for example, how to do the ComCam focal plane, which was used in the DP1 paper. So that's a result. So that first tutorial is based on that technical note. And as a reminder, the LSST camera is the largest digital camera in the world for astronomy with 3.2 gigapixels. It has 189 science charge coupled devices or CCDs, and they are arranged in 21 rafts. And each raft has 9 CCDs. But then, in addition to the science CCDs, we have 8 wavefront sensors and 8 guidance sensors in the corner rafts. So we have a total of 205 detectors. The focal plane covers about 9.6 square degrees field of view, so you can fit like 40 full moons in one snapshot, in one visit of the LSST cam. And each CCD is about 4,000 by 4,000 pixels, so you have about 16 million pixels per CCD. Each CCD is divided in 16 amplifiers because we want to read the camera very fast in less than a couple of seconds. The plate scale or the pixel scale is 0.2 R seconds per pixel on average. We have two types of CCDs by two vendors, produced by two vendors. One of them is called ITL or Imaging Technology Laboratory in Arizona, the University of Arizona, and the other vendor is Teledyne, and they produce another type of CCDs called E2B. All right, so the main package that is going to do a lot of the magic in this tutorial is called LSST.AFW camera geometry. So that's basically the takeaway. And also, if you need information, if you use the LSSTCam data or want to cite it in your papers, we do have a website for the LSSTCam, lssstcam.lsst.io, and then you find a cartoon and then some the filters and some technical documentation. So as a reference and a DOI to cite the camera that was built as LAC. Okay, so the first thing we're gonna do is we're gonna import our usual suspect of packages, matplotlib, but also this one that I was telling you was doing all the magic, in particular some useful routines that are gonna help us do the transformation between pixels and focal plane coordinates. We set up the color blind friendly plotting style at first. And then the first thing that we're gonna do here is gonna retrieve the LSST cam, the camera, the object. So we actually here imported the camera, the LSST cam is an object, and then there's a function that gives you the camera, and the camera is something that we're gonna be able to iterate over, and it's going to contain all of the detectors and all the information that we need. So one of the first things that we can do is just, of course, you can get the name programmatically, just like that, and the number of detectors, which, as I mentioned, is 205, the number of total detectors. So first, we're going to take a look at some properties that you can get from each detector. So you can pick a number. This is like an array. Here we pick number 94. And then the detector is gonna know information about its actual name, which is like a string that looks like this. It has like the raft number and then the CCD number. The CCD name is referred like this S11 or sensor, I guess. I don't know the S what stands for. But you can get the actual string. You can get an ID, which is a natural number, an integer number up to 205. And you can also get a physical type. As I said, we have ITL and E2B detectors. Um, the detector itself, you can also iterate over detectors, and then you get the amplifiers. So if you get the length of that detector object in this case, then you get the number of amplifiers, which is 16. And then some other details is that if you get detectors on the corner, you're gonna get if you have like a guided away from center sensor, you're gonna have the strings SG or SW in the name. Okay, so each detector also has, as we already explored some of the functions that it has, but then it has other interesting functions related to the actual physical sizes and measurements and location of the corners. So you can get the corners of that detector. You need to pass this focal plane object here that we already imported, and it gives you the relative coordinates of the relative positions of the four corners in this case. And all these functions and then are gonna be useful later when we do like a mega loop, like a loop over the rafts and the detectors in order to produce the focal plane. Then again, if you iterate in the detector, then you're gonna start looking into the amplifiers, and then each amplifier, if you explore that object, then it's gonna have some functions that tells you about the size, like the bounding box, for example, the name of the amplifier, which have these C names here. That's the official string names. And then also the height or the width that gives you the number of pixels per amplifier. So it's about 500 by 2000 pixels each amplifier. So then one of the things that we can do first in order to produce the focal plane plot is to group the detectors by raft. So we're going to define a dictionary here. We're going to loop over the camera object with detectors. We're going to get the name. Then this is like some regular expression mashing for the name, but I actually was thinking that maybe we don't need that. It's kind of general because we know that the name is actually going to be of the form like R22 underscore then S11 or something like that. So I guess you could just do a split here. But here basically we're doing is just getting the name of the raft to define the dictionary, and then in each entry of the dictionary we define an array to save the detectors. And then we can do another loop to count how many detectors we have per raft. Most of them have 9 detectors, and then other ones have 4, like the corner detectors. Okay. Then another set of important functions to help us do the focal plane plot are gonna be the transformation. So basically, this is already doing everything for us. So in this case, we take an example of a detector. We're going to look for one detector. We define a transformation between the pixels coordinates and focal plane coordinates. And then we can get an amplifier. We can get the box in pixels. And then we can use the transformation in order to convert to focal plane coordinates. For that, there is an intermediate step in which we need to convert to this point to the object, which is what this function is actually expecting. A lot of functions in the LSST science pipelines work like that, but that's just an intermediate step to convert the type of the coordinates so that the functions work. And then we do the printing of the corners. So in pixel coordinates, we have these integer numbers, but then in the coordinate system of the focal plane, we have something in millimeters. So in the end, okay, so now this last section, then so we can have some after a while a few questions and then move forward to the other tutorial. Um, we're gonna now make the focal plane of the LSSTCam. We defined a few helper functions here, just a few different colors depending on the type of the physical type ETL or E2B. This is another helper function that's going to give us the bounding box of a detector in the focal plane coordinates. It's another helping function here, and then another helping function that gives us like a rectangular patch defined by a bounding box, by a two-dimensional box. Okay, but it's actually using the patches um, function or object that's from matplotlib, I think. Yes. So that's what's gonna help us do all those rectangles that in the end we use. And that's it, basically. Well, then we have like the final loop. Let me see if I define the function. I haven't defined it. Let me define the functions. And then we're gonna have the final loop that is gonna give us the plot that we want. But then let's take a look at it. Okay, so this is what we get in the end. But then just go over here. You can go at your own uh, pace. But basically, we're doing a loop over the rafts, the dictionary that we defined, and each raft, remember, has a list of detectors. And then, okay, what's happening? We're plotting the box of the detectors. We get the raft center here in order to put the names of the actual raft. And then we do a loop for each detector list within each raft. We do a loop over the detectors. Then we use those helper functions that we defined before to get the bugs. Then we get a color, the name, everything that we're gonna want to put in there. And we do the transformation to go from the local pixel coordinates into the whole focal plane coordinates, so it helps us build the whole focal plane in physical coordinates. Here, this inner loop is over the amplifiers over each detector to help us do the little rectangles that we're gonna have drawn to identify each all the amplifiers within the detectors. So it's a few nested loops that use the helper functions that we define here and the other functions that each object has. So it's well, yeah. So that's it. We get something like this. I didn't make it interactive, but I guess you have some widgets or some other stuff that you could make it interactive and take a look in detail. But yeah, as I was saying, I usually come back to this plot very often to see which detector is which and the names and all that. And you can play around with it. For example, you can get just one draft if you want to get just one draft, and then you get like in ComCam. Let's see, if draft. I don't know. This is I don't me coding life. You know how that goes. Let's see if we can just plot. See, of course it didn't work, but uh, well, what I wanted to do is I just wanted to plot one, and I guess you just want to continue the loop, but I'm not good at coding live. But you can do that type of experimenting with this code. Okay, I think I want to leave some time for the other tutorial, which also has some important metadata from DP2. But yeah, this one is this. I hope it's useful. Do you have any comments or any questions so far? I don't see. Let me see. No one in the chat. You can feel free to talk to me while I change tutorials. Mhm. Okay, let's take a look at the other tutorial related to DP2. Um, and this one is, we have a file of visit and track metadata. And I want to emphasize that this is preliminary. As I said, officially, we should expect DP2 to be released between July and September of this year. That's the official word from RTN 011. We're going to use some sky projection packages here, and we're going to this tutorial basically accesses that data, that file of metadata, and then we're just gonna explore how to plot them, and then maybe hopefully give you ideas of what the type of science you can do with DP2 and help you prepare. For example, if you're thinking about a particular object clusters, I'm thinking, for example, about the type of galaxy clusters that are gonna overlap with DP2, etc., etc. So, okay, so we're gonna have a metadata of visits and tracks, and then one visit is one observation, one image, one exposure with the LSSTCam centered on a given coordinate and obtaining a single filter and sky rotation. One track is a square region of the LSST's all sky tessellation, which is called a sky map. and it's about 1.66 degrees per side. And then each tract is subdivided into 100 patches. We call them patches, and the patches overlap between them. So one deep coat image, which is one of the data products that we get in the end, is created per patch. Okay, so you find there is a website actually that has like a more detailed information about the type of survey validation and commissioning that has been happening since last year with LSSTCam. So it's linked there if you wanna read a little bit more about it. But basically, um, the information that we're using in this tutorial is based on what is summarized here, which is basically also telling us what our colleagues in Rubin have been doing for doing commissioning and science validation. I was going to say verification, validation of the LSST. So that's an important source to take a look at. Um, if you read in detail, I believe the initial um, like area for DP2, the initial plan area was going to be about 3,000 square degrees, but then there were some changes in plans, and then we had to focus on about 750 degrees. So we're going to have like more visits in this inner 750 degrees square degrees area. And also you can see some deep fields here that are red. But okay, I guess I'm getting ahead of myself because basically we're going to do some plots like that. So all right, we start importing our packages. Let me actually, I don't, I was running this. Let me start from zero. Let's clear the kernel and clear everything, and let's start from zero, so I don't have any safe variable or something like that over there. Okay, so we plot we're gonna use some functions from AstroPy, including the WCS, sky coordinate to do some matching with objects, matplotlib as usual, sky projection to sky prog to the sky projection, helpix, helpy for helpixes, and then we have the plot, the lines and the symbols and the styles for the LSST that you can just import them right there. So here we define the parameters, and then here this is the file actually where we have sorry, this is the path to that public data where we're gonna find the file that we're gonna use here. One option here, we could stick with matplotlib, which is static, but then there's something cool called widget here that is gonna allow us to do some interactive zooming of each file of each plot. And then this is the file that you can just go and copy it, right? You can go to this path. That's the name of the file. Actually, we have, yeah, well, that's one of the files that we're going to use here. And then this is the type of information that you're going to find there, the visit ID, the filter, the band, the coordinates, right ascension, declination, the camera rotation, azimuth, altitude, the distance to the zenith. Then you have interesting stuff like the Air Max for the telescope pointing, the exposure time, the time at the middle of the exposure, the time at the start of the exposure, and then you have some image quality quantities called mean seen and mean maglim, the magnitude limit. Okay, so here you're gonna tell me, oh, Andres, there's already a typo. Yes, there is a typo. So the actual file, like recently before this tutorial, we updated the file to add these image quality columns. So it differs a little bit from what's here. So that's note to myself to fix that. So that's a little typo here, but that's something small. We're reading that file. I already ran it, and you see what we have, the type of numbers. You can explore the plot. And we can start by looking at the exposure times. By filter, you see most of them are 30 seconds. GRIZY, then U actually goes to more than 35 seconds, and then you even have some exposures with less than that. But this is a coarse binning, so you can actually play around with changing the binning, or actually this interactive plot widget lets us do like some zoom in like this. And then you can see that actually the ones that have 16 seconds are in only these bands for whatever reason. I don't know why. So we can go back to home here and then do zooming and exploring. I thought that was cool. I usually don't use this zooming thing, but for example, here you can tell that there's a little bit of I and R. There's more of G, and then most of them are in U band as expected. That's the exposure times histogram. Then we can do here some more detailed statistics of actually like the mean exposure time and the number of exposures in each band that actually have a particular amount of exposure time greater than or less than 30 seconds. So of course you can explore the data and do a little bit more of fine exploration of it. So, but then that's related to exposure time. Then we're gonna have the modified Julian dates, so the time at this at the midpoint time of all the exposures. And then we can start doing some histograms like this. So this is actually a cumulative distribution. Then you get the number of, as you can see, then you can identify the actual period of calendar time for the data, for the data that corresponds to the metadata in this file. So that would be April 25 of last year to June 7. Then you can identify certain periods in which more data was taken. Then I think there was like some engineering period in which we didn't take much data. So et cetera, et cetera. You can take a look at that from that cumulative distribution. Here you can do something similar, but by band. You can see how maybe, for example, this U band here up to a certain point in time, then we started focusing on other bands and not so much on U band. The I band had a more or less constant focus of taking more data in those bands. So you can take a look at that. Also, depending on the type of science that you want to do, you're maybe more interested in all the bands and in certain bands than other. Another useful plot is going to be the distribution of the cumulative distribution of air mass that you can see. It's very steep at the beginning, which I guess is good. We want to observe as much as possible closer to the zenith, but that depends on many factors, of course. But we have this steep increase as a function of air mass and the number of visits, which is something expected. So that's another important plot right there. This one, similar to what we had before, we focus now on the number of the type of filter and the distribution with air mass. And then you can start thinking about things like, I don't know, chromatic scene. I usually, think about the PSF depending on the air mass and stuff like that, depending on what you want to take a look at. Okay, then a few image quality estimates. Maybe some of you saw the community post by Bob Blum recently, I think last week, sharing some image quality histograms as well. But then here we have a way of visualizing that as well. For example, in these plots, we have a cumulative distribution of the mean seen as a function of band. Then you can see here how we're maybe closer to many of them closer to one, which is consistent with what Bob was telling us. And then also this second plot is the magnitude limit for each filter. So we're using those IQ columns that I was mentioning before here in order to do those plots. Those are the two in image quality that are actually in turn estimated from survey property maps. So yeah, this is a way of visualizing that information, the depth. And now we can also take a look at the sky distribution. Here we're gonna use the HillPy package. We're gonna, for this particular visualization, we're gonna use hill peaks with n site equals 19. And when you choose that n site parameter in hill peaks, equals to 19, it actually gives you a cell or a hill peaks whose field of view is similar to the LSSTCam field of view. So you get about 9.52 square degrees compared to 9.6. So just was chosen, so it's like that. So yeah, so here you can start looking again at the distribution of visits, and the spatial distribution of the data in this case. Actually, this morning I was taking a look at this and looking at the hypersupreme camera footprint because I want to do some science with that. So this is the kind of thing that you can start doing as well. I think you can zoom in with this. Yeah, you can, but it's a little bit slow with the widget. I usually don't use widget, but I was just curious. Okay, so that's a useful plot that you can do. You can predict the approximately total sky area covered by these visits. So here you can see that this is like all the visits is actually covering like a lot, right? But it's gonna have a different number of visits. So initially I was talking about 3,000 square degrees, but that's mostly like here. Then a subset of that, the 750 square degrees are gonna have like more visits that is gonna be covered here in the yellow. But actually, technically, from what we have in this file, and we can say that this is DP2 or so far, then technically you have all these sky coverage, but you're not gonna have the same amount of visits in each case, the same depth. Yeah. Then again, this is preliminary. I just want to say it over and over again because there's going to be like different types of quality cuts. Things might change from here until the DP2 is officially released. Here we're plotting something similar to what we were plotting here. This is actually with all the filters combined. Actually, I skipped that one, all the filters combined. And this is just like one filter. In this case is the G band, I believe. Yes. So you can do this, you can play this game with per filter and also gives you an idea. Um, okay, so this one, it says that it might take a few minutes, so I'm gonna skip it because it shows, I guess, the option to mark each visit as a separate marker. Oh, yeah, I guess you get a plot similar to this, but like with visits also they're marked, but I'm gonna skip it because it's gonna take a few minutes. Okay, so then you can take a look at the tracks. I need to change the name of the file here again, but it does, anyhow, the point is that the file does have some information, again, about the tracks, track ID, the filter list, the corners in degrees, the phi sigma PSF point spread function magnitude limit in the R and I band. These are AB magnitudes and the characteristic width of the PSF. As I was mentioning, these properties, these quality parameters, image quality parameters are derived from the survey property maps at the center of the tract. For DP1, we do have like a couple of tutorials that demonstrate the use of survey property maps. As a reminder, the plate scale of zero point 0.2 arcseconds per pixels. And then we have the usual formula to convert from full width of half maximums from sigma to in pixels to full width at half maximum in a square, I'm sorry, in arcseconds. So we're gonna read the table, which is this one with IQ. Need to change that. So you can count the number of tracks, about 2,200, number of square degrees. And then let's see what's happening here. This is the number of tracks covered in all 6 vectors, yes, with the area covered as well. Okay, so here, yeah, here we're just plotting again the track table first. And then we can take a look at the coverage by filter. I guess we have um, then this says some tracks are not fully filled by the deep coat images. Okay, so yeah, so that's why they have like some NaN values. And then they show us like the total number and the fraction of the R and I band tracks that they have that have sufficient data for the PSF magnitude limit to be estimated. Okay, some more details here. Then we have the image quality histograms that we can make, the cumulative distributions in the R and I bands. So it gives us an estimation of the depth. And then again, this is already useful. I was this morning with a colleague talking about like, are these data gonna be deeper than HSE or not? So you can start answering that type of questions. And it's also gonna be important the type of the R second. So consistent with what Bob was saying and the image quality that we're getting of a median of a mean of about 1 R second. It of course depends on the filter in which you take a look at this. All right, then we have some sky distribution here. So we're gonna have like one polygon per tract. So another way of visualizing things, but with tracks. You can do it now for one filter. And then we're gonna have the DP2 tracks for which the R-band deep coat images still exist. And then you can also start playing with, for example, oh, I guess I was clicking on here, but I was gonna say that of course, if you can put the cuts that you want, and in this case, you put a cut on the magnitude limit on the PSF that is greater than 23, so it gives you the information as well. This is another useful example, like is my object in DP2? Once again, we have the caveat that this is a temporary, but still it's still useful and hopefully gives you an idea and helps you plan to start doing science with DP2. So here we're gonna just define two target coordinates. And as an example, these are just to show that, so one of them is by constructions in the footprint, the other one is not. We're going to use AstroPy sky coordinate to convert them to that type of objects because that's going to help us with the data manipulation. We define a radius of the visits, which is the radio of the LSSTCam field of view. Then we convert the visits coordinates to this sky coordinates class. So in order to do the matching and we do apples to apples comparisons, then we just need to convert everything to the same type of coordinates. And then because it also has very handy functions that calculate already the separation between points in the celestial sphere. And then you just need to see if things are inside or outside of what you're looking for. Well, in this case, we're counting the number of visits that contain target number one, and then here we're containing the number of visits that contain target number two. And then as we were expecting this one of them is in the footprint and the other one is not. All right, we do some cleaning here. Now we're gonna take a look at the tracks here. And here we're gonna define a third target that is actually within the first track's vertices, and then when we convert that to sky coordinates. And there's a method actually here in the region of the sky that we're defining here. So let's go back a little bit here. We're gonna get the vertices from the tracks table. We're gonna get the coordinates, convert to sky coordinates, and then we define a polygon a sky region, a polygon sky region with those vertices. So that's what's happening. And then we're gonna use a method of that region sky that's actually telling us whether the target is within or not that region. So that's what we're doing here. Um, So one detail here is that it requires the use of a world coordinate system to be passed. So we create like a generic coordinate WCS here from AstroPy as well, but then in the end it helps us see if the points are within the region of the sky that we define above or not. Okay, So yeah, what is this? Mhm. So so for each one of these ones, then we are gonna check if any tracks overlap. Um, and then we're gonna find that yes, we do have overlapping tracks for the two of those targets, but not for the second one. Okay, we're almost done, and then we have some time for comments and actually any questions. So here we're gonna combine the visits and tracks and maps and everything in a single plot, and then we're gonna put the location of these targets here. So for these three targets, yeah, you can see the location. One of them here is in one region that's closer to a deep field. I imagine it looks by the number of visits. Another one that is actually right here in the center, and then the other one that is not included. So you can do this type of visualization as well. Then another cool thing that you can do is that you've already been working with DP1, writing papers with DP1. So hopefully you're all familiar with the 7 fields that we had. So we can retrieve the coordinates of the center of those fields. We can find them in the DP1 tutorials. Then we can see how many visits overlap in DP2. In this data that we have for DP2, how many of them overlap with those fields from data preview 1. You're gonna see like a spoiler alert that most of them are actually we have an overlap with the extragalactic field, the Chandra Deep Field South and the Euclid Deep Field South, but not so much with the other ones. And then is there a deep coat tract that overlaps with the center of a particular field? So it's telling us um, the overlap, yeah, between this deep coat is there is a tract of the deep coat that overlaps with the center coordinate of that field. So as I was saying, it was mainly the extragalactic fields actually that have the overlap. These two here. And then to finalize, we can do a plot similar to what we had before, but now putting the centers of the fields. Let me see. Takes a little bit of time with the widget interactive plotting, but yeah, I don't know why what is cut. The legend here is a little bit cut, but yeah, but these are the fields. I mean, I need to take a look at that and see if there's a bug, or we can just plot it with matplotlib and then it'll be fine. But the DP1 tutorials it also has the location of the DP1 fields. Okay, so I guess these two are the extragalactic fields right here, the star and the triangle. Okay, thank you. I hope you can have fun with these tutorials, in particular the DP2 one, the metadata. Keep in mind that it's preliminary, but yeah, looking forward to hearing and seeing what you're gonna do with this data. I think we have some time for questions and comments. And if not, we can always leave early. That's always nice. No, but we have time, so let me know what you think. Is this notebook intended only for stationary sources, or can it also be used for moving solar system objects like asteroids and comets? I guess in this case it was pretty static. I'm not like actually like a solar system expert here, but um, yeah, I don't know. I would imagine if there is coverage overlap with the ecliptic or something like that. I don't think we have, I don't know if we have like a lot of information about the solar system objects in this metadata here. It's mainly about survey properties and spatial coverage. Um, I'm trying to think. Otherwise, I don't know if I have some of my solar system experts friends from the CST in the call, but if not, I can follow up and see what type of information from the solar system. we can find. I know that we have the alerts right now, like some of the alerts and are there. There are some brokers, like primary brokers and downstream brokers. I think Snaps is the solar system one. But in this case, yeah, it's like this metadata that as I was mentioning, more about survey properties and some image quality. Ismael, do the deep coat regions have templates already for alert production? Um, that I don't know. I would think they do have. Yeah, in particular, we are building. I know officially from the documents that definitely the commissioning and science validation data is used to bootstraps us to get the first templates for the first data releases. But I would need to check if there is any official like a statement about that. I also need to be careful about what I say officially and not. But from what I remember, that's in the policy in the documents that yes, that templates are being built. But that's something also that I can double check in terms of the templates. And then we have yeah, thank you for the question, Ismael. Then Jamie Robinson, you would have to match the predicted ephemerides of your asteroid comet with the position and time of the DP2 pointing. Right, so that's I guess something that I was also kind of thinking, yes. So thank you. That's related to the solar system question. So you have information about the time of the pointing, and then I guess to a certain point, you know where things are gonna be or where in time. Um, Thank you. Remember that next week we also have a DP2 question session with Lian Gi, and I posted the link to a Google form. I'm gonna post it again where you can submit your questions in advance, and Lian would love to have your questions in advance to address them. These are great questions. Yeah, and please spread the word about this session as well. With Lian. Um, do we have any more comments or any more questions? Mm, okay, going once, going twice. Thank you so much again for coming. And okay, we'll stop here and we'll see you next time. Thank you, everyone. Bye bye.